Congratulations, you've recently survived the 2025 AP Physics 2 exam. And being the high achieving students that you are, July is just too far away and you need to know how you did. Well, I'm here to help you out, and I'm going to do a little walkthrough of the FRQ section here so that you can see, and compare yourself to how you did. And I'll note that I only glance at these problems a little bit. I'm going to do them blind, just as blind as if I were taking the test for the first time. And so if I make a mistake, feel free to complain about it in the comments. All right, problem one. We have two very long wires with current running in the positive x direction. They're parallel to each other and separated by a distance d. It points out that there's a point P located at the center of wire 1 here, which we're defining as the origin. We're starting out. It asked us to complete the following tasks in the figures below. We're either going to use arrows or the symbols for into the page or out of the page. And we're going to indicate the direction of the magnetic field from wire 2 at point P. We're also going to indicate the direction of the magnetic force that's exerted on wire 1 by wire 2. So we have a magnetism problem at our hands, and we're going to use all of the right-hand rules we have at our disposal to figure this out. To find the field at wire 2, we're going to apply what I call the right-hand rule number 2 for finding the field from a moving charged particle. We're going to point our thumb in the direction of the current, and we're going to curl our fingers around until they touch point P. And when I do that, you can see that they're pointing into the page. So that's an easy one. We're just going to write a little X in the box for figure 2 to represent the field is into the page at that point. For the magnetic force on wire 1 by wire 2, we have a little shortcut we might remember, where if we have two wires where the current is going in the same direction, we know that they're going to attract each other. So the force should be upward. If we don't remember that little shortcut, we can use the other right-hand rule, where we're going to first point our finger in the direction of the current. We're going to contort our hand a little bit so our fingers point in the B field down directly into the page. And now, just like some kind of science Jedi, the force is pointing out of my palm upward, as we suggested before. So we can draw an upward pointing arrow for the force. And that does it for part 1. If we move on to part 2, we're bringing a third wire to the party. It's carrying a current of 2I in the same plus x direction as the others. It is located at a coordinate y equals y3. It tells us the net magnetic force exerted on wire 1 by 2 and 3 is 0. We want to find an expression for y3 in terms of the distance d. So we need to begin our derivation by writing a fundamental physics principle or an equation from the reference information. So I would start by doing Newton's second law. We have F net equals ma. Since the object says the net force is 0, we're in equilibrium, and thus we can set the force from wire 2 minus the force from wire 3 in the other direction as equal to that 0. In other words, these two forces cancel each other out on wire 1. For that to happen, if these are all pointing in the same direction to the right, and we can label these 1, 2, and 3, 3 has to be located below wire 1 in order for it to kind of attract wire 1 the other way. Remember, we said wires in the same direction will attract. So 2 is attracting it upward, 3 will attract it down, and that will give us the cancellation of forces we need. So we have to figure out, how do I write the magnetic force from these wires? Well, the magnetic force on a wire is equal to the current in that wire that we're acting on, the length of the wire. Here it's infinitely long, so we can effectively just kind of ignore that length. It'll cancel out anyway. And then the magnetic field that it's in. So for each wire 2 and 3, there's going to be a different magnetic field that will be exerted on 1. So in order for this to work, we need to get rid of that B. We need a way to write the magnetic field from a wire. Well, that's on our equation sheet. We can find it as mu naught. Mu naught's the permeability of free space. That's a constant. We have the current of the wire producing the field. And then we have 2 pi, I guess we'll say d in this case, where d is the distance between the wire and wire 1. So for each of our forces 1 and 2, we're going to take I, L, and substitute in the B for that current. So force 2, remember we're acting on I1, has a length L, and we're going to use the magnetic field from wire 2. So that's going to be mu I2 over 2 pi d is the distance between wires 1 and 2. F3, on the other hand, it's going to start out a little the same, I1 times L. We still have a mu naught. We have I2 as a value of I, by the way, because I3 has a value of 2I. We're going to divide that by 2 pi y3, the distance we're trying to find. Now I'm going to set these equal to each other, and almost everything cancels out except the d in the denominator, the y3 in the denominator over here, and we have a 2 up top. Everything else vanishes. So when I set F2 equal to F3, we end up with 1 over d equals 2 over y3. We can cross multiply to solve for y3, and we'll get y3 is equal to 2d. And we'll note that this is below the origin. So it's negative 2d, I guess. That makes sense. If the current is twice as strong, we can expect it to be twice as far away and still influence the wire just as well as wire 2 did. So there you go. 2d below the origin. Let's move on. Now we've taken y3 away, so it's moved very, very far away. It's just a fancy way of saying ignore everything that happened in the previous part. And we're back to our 2 wires pointing to the right. We put a little metal loop below the plane, and then we move the loop at a constant speed downward in the negative y direction. It asked us to indicate whether there is a clockwise induced current in the loop, counterclockwise, or no current induced at all. So this is an application of Faraday's law and Lenz's law, which says that the induced current times R, I guess, is equal to the opposite of the change in magnetic flux with respect to time. So we want to think about, does the magnetic flux going through this loop change as we move the wire away, or move the loop away? Our right-hand rule tells us that from both wires, when we curl our fingers down below, the field is pointing in to the loop. So we can remind ourselves the field, little x's, that it's pointing into the loop there. But also from our magnetic field formula, magnetic field scaled with 1 over d, the distance from the wire. So we expect the magnetic field to get weaker and weaker the further we get away. So the flux indeed will change. It should get smaller. So we expect the flux to decrease as that loop moves away. So how do we figure out the current? We're going to first define a coordinate system for what a positive current looks like. So the way we do that is we're going to point our thumb in the direction of the magnetic field into the page, and we're going to curl our fingers around. And so what this tells us is that a positive current will flow in the clockwise direction. Our thumb goes in with the B field into the page, fingers curl around. We're going to call this I plus. Now, just be careful. This isn't the answer. We're just providing a reference from that we're going to use to deduce the answer. This is the direction that a positive current should flow, should we need to. To figure out if that's true, basically this says if the flux decreases, the change in flux is negative rather, then the negative sign from delta phi b is going to cancel out with the negative sign there, and it will be positive. So the flux decreasing means the current should flow in the positive direction, which means it will flow clockwise in the direction we specified with our right-hand rule. So it is clockwise. Check. Justify our answer. I guess I kind of did that up there, but we could say B field is into page and decreases with distance. As loop moves, B field weakens. and flux decreases. The current flows clockwise to oppose this change in flux. And really, again, what it's doing, when the current flows clockwise, if we do right-hand rule with that current, the magnetic field that current generates is out of the page. So the flux is getting weaker and weaker. This way, we generate a current to oppose that change and get us back to kind of where we started. So induced B field opposes change in flux. Hooray! And that does it for problem 1. We're a quarter of the way there. Problem 2. We have a sample of monatomic ideal gas in a thermally conducting container held by a movable piston of mass M and area A. So this piston here has a mass M and an area A, the cross section across from it. The container is in a large water bath that's held at constant temperature T0. The piston is free to move with negligible friction, and at the instant shown here, the gas is in thermal equilibrium with the water bath. The piston is at rest, and the gas occupies a volume V0. There is an atmospheric pressure above the piston, PATM. So what we want to do is draw a force diagram on the piston, labeling all forces that are acting on it. Everything should be in equilibrium at this point. And so we have the obvious force of the weight acting downwards, Fg. We also have a force of the atmospheric pressure on the outside of the container pushing down as well. So the force of the atmosphere. And then I'll draw a much larger vector up for the force of the gas on the inside pushing opposite that. So if we want this piston to be in equilibrium, it's not moving, then our largest force is upward from the gas inside the piston, which is balanced with the combined forces of gravity and atmospheric pressure pushing downward. So a nice little force diagram to start us off. In part B, it wants us to derive an expression for the internal energy of the gas in terms of the mass, the area, volume, and the atmospheric pressure, and physical constants as appropriate. We're going to begin our derivation by writing a fundamental physics principle or equation from the reference information. So again, we can start off with Newton's second law here. We've already been kind of teed up with our force diagram. If this is in equilibrium, then we have that the force of the gas upward is minus Fg minus the force of Atm. We want to write this in terms of the atmospheric pressure, not the force due to the atmospheric pressure. So one, we use the relationship that pressure is equal to force over an area. So we can rewrite F as PA, and we can do that for both the gas and the ATM. So the pressure exerted by the gas, PA, is equal to mass of the lid, big M, times G, plus PATM times the cross-sectional area. So that's a way to balance our forces here. We ultimately want to find an expression for the internal energy. So U, according to our equation sheet, is 3/2 NkBT. If we note carefully, we might see that this structure here, NkBT, is the right-hand side of our ideal gas law, PV equals NkBT. So that is the pressure of the gas times the volume V0. We're not allowed to use pressure of the gas directly, so we're going to eliminate using that using the Newton's second law expression we set up. We're going to divide both sides by A, and we'll substitute that expression in. So P gas is going to be mg over A plus PATM. So we put all of that together. We get mg over A plus PATM times the initial volume times 3/2. And now this is all in terms of the variables we're allowed to have. We have M in there, we have A in there, we have V0, PATM, the 3/2 are some physical constants, and so we are good. This satisfies exactly what we want for part B. So 3/2 times V0 times the quantity, mass times G over A plus atmospheric pressure. In part C, we have another block of mass M is placed on the piston at time t equals 0 and is slowly lowered. The piston comes to rest at t equals tf when the block is completely released. On the axes provided, sketch the expected relationship between the pressure and the volume of the gas for the thermodynamic process that the gas undergoes during the time interval t0 to t final. Draw an arrow on your sketch to represent the direction of the thermodynamic process. So what happens here is the block slowly lowers the piston, and then the system comes to rest once the block is fully on top of the thing. So what's happening is we are decreasing the volume of the container. That is going to increase the pressure. We are going to start in a high volume state with lower pressure to represent when the container is expanded, and it's going to squeeze down to lower volume, increasing the pressure along the way. The water bath keeps us at constant temperature, and so we have this nice inverse relationship, swoopy curve of a graph there. And we're going to start here at point A, go to point B, so we draw the arrow that points leftward along that curve. The next part says, with the block still in the piston, the temperature of the water bath changes to a new constant temperature. The gas occupies the original volume, and it comes back to a thermal equilibrium. We want to know if this new temperature is greater than or less than. It is, in fact, going to be greater. The reason we know that is we want to go back to our answer in part B, our equation that had the internal energy of the system as 3/2 V0 mg over A minus the atmospheric, or plus the atmospheric pressure. And our new system, the block is still on there. The mass of our system is increased, so M goes up. U and M are inversely proportional, so U is going to go up. U is essentially synonymous with temperature. Anything that happens with U will happen with temperature as well. So since the internal energy goes up, the temperature goes up as well. And so the new temperature is greater than the original temperature. So that takes us to the end of part D, and with that, the end of this thermodynamics question. We move on to looks like a circuits problem, and it looks like it is a lab design question. Everybody loves those. We have in experiment 1, a student's given a resistor of unknown resistance and an air-filled parallel plate capacitor of unknown capacitance. So we neither know R or C. We're asked to predict with the expected time constant tau of a circuit if these two circuit elements were connected in series with a battery. The student has access to a battery of known EMF, that's voltage, a switch, an ammeter, a ruler, and wires. So all the stuff we have is pictured here. The plates of the capacitor are squared and the separation is small. The capacitor is initially uncharged. Assumed dielectric constant of air is 1. So we want to describe a procedure that would allow us to find the time constant tau. In our description, include the measurements to be made and any steps to reduce experimental uncertainty. So I believe what we want to do is we want to construct a series circuit where we have our battery, here. This is the battery. We're going to connect to our battery in series. Let's put the switch in there. We're also going to connect our unknown resistor, R, and our unknown capacitor, both in series. The wires are the linear part connecting each component. So we're using all these things here. We're going to finish our circuit by putting an ammeter. It's really important that we place the ammeter in series. That's how we're going to measure the current in both the resistor and the capacitor at the same time. Ammeters needs to be in series with those components. And then we complete our circuit like that. So our procedure that we might use here is going to be set it up like this. We are going to close the switch to start things off. And then we are going to monitor the ammeter until it reaches 0 current. Then we're going to turn off the switch. While we're doing this, we should be using a stopwatch to measure the time from closing the switch to when the ammeter reads 0. We always want to make sure that we're doing multiple trials to reduce error, so we should just say multiple, or do this. I don't know, let's be cheeky and say 100 times to reduce error. I always tell my students that no matter what the lab design question is, if you have no idea how to do it, you always just write, I don't know, but I would do it multiple times to reduce error, and you will get a point. So make sure that you have done that. So how do we use this data? What's going to happen is the capacitor is fully charged when the current is 0. In other words, a fully charged capacitor will match the voltage supplied by the battery and prevent current from flowing through the circuit. There's a rule of thumb, because a capacitor charges in an exponential fashion, the charging time is approximately equal to 5 times tau. So if I've measured the time it takes to charge, I'm going to take the average of those from all my 100 trials here, and then I'm going to divide that result by 5. Divide charging time by 5 to get tau. That's our time constant. So not too shabby. We construct a circuit, we use the ammeter to monitor the current and figure out how long it takes for that capacitor to charge, aka the current goes to 0. We use a nice rule of thumb that tau, the charging time, is roughly equal to 5 times, the charging time is 5 times tau that we're looking for. So we can divide our result by the 5 to get the tau we want. A different group of students are doing experiment 2, and they're asked to determine the capacitance of a different parallel plate capacitor. For each trial, they look at the potential difference across the plates and the charge stored on one of the plates. And we have the following data. It tells us to indicate 2 quantities that could be measured so that we can determine C. So we're going to use our definition of capacitance as the charge per unit applied voltage. And so if we have the charge on our vertical axis and the potential difference on our horizontal axis, then look, if we map this to a linear equation, the charge plays the role of the dependent variable of y. The voltage plays the role of the independent variable x, which means if we're mapping this to a linear equation, our slope is just the capacitance. So we're just going to plot Q on the vertical axis, potential difference on the horizontal axis, and the slope of that line will be the capacitance we want. So slope is capacitance. It gives us a grid and says we're actually going to plot those things. So we said we wanted Q, and this is going to be in times 10 to the negative 10 coulombs, according to our scaling in the data table there. Our potential difference will be on the x-axis, just measured in volts. And I want to choose a scale that will get all of my data in. We want to make sure we use at least half the graph provided. We don't want to cram everything into a single square at the bottom left corner. Our data goes from 3 to 10 for the v-axis, and so we'll probably just end that around 10 or 12 or something like that. And then Q goes from 0 to 8. So let's just put a 10 on both axes. And count out, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So we'll just go every 3 will be 1 unit, starting 0 at the corner. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then we'll do the same thing for our vertical axis. 1, 2, 3, 4. It's always best to not skip, because even though like our charge starts at 3, it's nice to go from 0 so you can really see where the origin is. They like that. So maybe you can earn brownie points for doing something like that. Oops, put the 4 too close. Make sure that they are evenly spaced. So don't do what I just did. I'm teaching by example here. It's very hard to count squares, so I don't envy you in a tense test-taking time. Should end up right at the corner. Great. Whew. So now we're going to carefully plot our data. Our first one's at 3 and 2.4. So I'll be on the 3 line for V. We go a little bit less than halfway between the two. Then we have 5 and 4.2. So we go to the 5 line. We go just a little bit less than a third of the way. So each square is a third. 7.2 and 5.6. So we kind of go to the second line here. 7.2 be there. We have 8 and 6.6. Yeah, 8 and 6.6. And then finally 10 and 8, nice and on the grid lines. So we have a nice linear looking piece of data here. We need to draw a line of best fit, because it says draw a line of best fit for the data graph in part C. Always use a straight edge to the best of your ability. Your goal, again, you're drawing this by hand. If you want to use a regression function in your calculator, you can do that. You'll need to write I did regression to get the points. But you want to try to draw this so that you have an equal number of points above and below your line. So maybe something like this. They're going to be pretty lenient on how exactly your line is formed, as long as it looks like it passes through your data. That looks pretty close. I've got 1, 2 below the line, 1, 2 above the line. That one's on the line. And that looks like a good representative of my data. Now, I want to pick 2 points actually on my line, and I want to find the slope based off those points. So the trap to fall into is you pick 2 data points that you like from your data table and you just subtract those, but then you're going to get a different slope than you actually want. So try to find points on your line that are on grid line. So maybe right here is good, and also right here. So neither of those are in my data table. The y values, this looks like it is at 5.66 and directly at 7. Sorry, it's at the 0.7, 5.66. And this one is at 5.33, 4.33. So now we do our rise over run, delta Q over delta V. We are going to get, remember our units, the Q is times 10 to the negative 10. So delta Q is going to be 5.66 times 10 to the minus 10 minus 4.33 times 10 to the minus 10 over 7 minus 5.33. So if I do the subtraction here, I should get 1.33 times 10 to the negative 10 over 1.66. And this roughly simplifies to about 0.8 times 10 to the negative 10 farads is our units for capacitance. And I would just leave it there. I wouldn't try to convert it into any other units. Again, there's many possible values you could get for this. As long as you're in the range of about this, you should get full credit. So that is the lab design, drawing a line of best fit and interpreting the slope question they always have. And now there's one more to go. So it looks like we have a optic, specifically diffraction and interference with thin slits. We have 2 narrow slits, distance d apart, so we're in a 2-slit experiment. A screen is located at distance L from the midpoint, and L is described as much, much, much larger than D. We're going to shoot a laser toward the slits, and we're going to see a interference pattern on the screen, bunch of bright bands and dark bands. It puts our attention to that there's a bright band labeled A and a bright band labeled B down here. A student claims that the distance between the center of band A and the center of the central bright band is smaller when using a laser that emits violet light than when using a laser that emits red light. That sounds reasonable. We want to indicate whether the student's claim is correct or incorrect without manipulating equations. Justify our answer by referencing the distance in path length traveled by the light from each slit to the center. So the idea here is those bright spots are caused when the light from the top slit and the light from the bottom slit interfere constructively. This means that their path difference is an exact integer multiple of the wavelength of lambda. The idea is if this is our screen over here, we're looking for, how much further did the bottom path cover than the top path? The path difference, again, if this is very large, we can kind of pretend these lines are parallel. They're not, but they're pretty close when that distance gets pretty large. And so we're looking at just kind of this path difference here. The bottom one goes a little bit further, and we're going to get a bright spot when this little path difference is an exact multiple of the wavelength. Well, if we're comparing violet light versus red light, violet light is on the kind of bluer violet side of the spectrum, and so that is associated with a smaller wavelength. And red light has a larger wavelength. So we would expect the first integer multiple that creates this dot to be smaller, a smaller path difference just because the wavelengths themselves are smaller. We would expect the criteria to get that integer multiple would occur earlier than it would for a larger wavelength. So the student claim is on the ball. Violet light would create a smaller band because it has a smaller wavelength. This allows the path differences to be smaller. To produce constructive interference. All right, that's part A down. Part B says derive an expression for the distance between the centers of slits, bands A and B, when light frequency F is emitted towards the slits. Express our answer in terms of D, L, F, and physical constants as appropriate. So remember, our answer can only have D, L, and F and things like pi and C, the speed of light, and H bar, maybe, if that were in there. So we're going to begin our derivation by writing a fundamental physics principle or an equation from the reference information. We want to note that we are looking at our bright band A, which is 1, 2 bright spots away from the center. So if we think about our equation for constructive interference from two slits, it's going to look something like we need an integer multiple of a wavelength is equal to d sine theta. However, we're not allowed to have lambda. I guess we're not even really allowed to have m, but we can note that m is equal to 2. So we need to replace lambda, and we also need to replace this angular dependence because that's not one of the allowed variables. So note we want it in terms of frequency and not wavelength. We're going to use the relationship that the frequency is equal to the wave speed. Here we're talking about light, so we're just going to be the constant c, the speed of light. That is allowed as a physical constant, divided by the wavelength. So we can replace our wavelength with c over f, and we should do that in our equation. I'll replace the m with a 2. 2c over f. Now the left-hand side is completely kosher, and we need to get rid of the angular dependence there. When our length, d, is much, much smaller than the spacing between the slits and the screen, that means that the angles that we're going to get are really, really small. So we're going to employ what's called the small angle approximation. Which, to explain where it comes from, requires the dark arts of calculus. So I'll just cut to the chase and say, in this case, the distance y that the slit appears from the center of the screen is equal to, the angle that the slit appears from the screen is y, this kind of vertical distance from the center of our system, divided by L. So we're going to replace sine theta with that, and we get y over L. If we now solve for y, we're going to get 2cl over df. It's worth noting that this y was from the center out. If we want to find the distance between the two spots on either side, we just need to multiply this answer by 2. So distance between A and B is 2 times y. So we're just going to multiply this by 2 and get 4cl over f. I'll call that DAB. So that's our expression. And then we check. Does this represent a distance? I have a speed divided by a frequency. That is a wavelength. That's a length. I also have this length divided by a different length. So unit-wise, this is units of length. That's good. It's also only in terms of DL and F with some numbers and constants thrown in for good measure. All right, we've almost made it. The final part of the test. Part C says indicate whether the expression you derived in part B is or is not consistent with your answer from part A. Briefly justify your answer. So do exactly what it says. Let's go back to part A. We said that violet light would create a smaller band because it has a smaller wavelength. We also know that smaller wavelength correlates to large frequency. So if we have a smaller wavelength, violet light, that's naturally going to have a larger frequency. And we can see because F is in the denominator, as F grows, DAB is going to get smaller, which, yes, it does agree. If you got part B completely wrong and you ended up with something like DA equals 4CLF, I don't know how you get that, but let's say you did. You would want to say, no, it doesn't agree with the statement from part A. As F gets bigger, D also gets bigger. They just want to see that you know what your equation means. You don't necessarily need to get the right answer. You just need to be able to interpret your answer, whatever it is. So in this case, you would say F increases, D increases. That's the opposite of what the student said before, so no, it doesn't agree. That being said, I hope you did get the right answer and that you were able to just say, what we said over here on the left. All right, we did it. That was the whole test. I hope that there are many 4s and 5s in your future and that this was helpful for you to see where you lie. If you're viewing this video from the future and you're trying to prepare for a test that is not in 2025, I hope you also found this as a nice, helpful study aid.